This is the general layout of our NONLIN software. This layout can be divided into 5 parts. First is unit declaration part, where we decide what units we want to use. Then force declaration part, where we define the different forces that are going to be applied on our single degree of freedom system. Then we have our singled off system. Here we give the mass and damping as input. Then we have system properties. Here we actually decide whether our system is to be analyzed as a linear case or a non-linear case, and then we give the different parameters that are required for those analysis. And in the fifth part, we see the outputs like periods and frequencies and so on and so forth. So let us say we want to analyze a singled off system and we want to find the ductility factor for that scene. So first we'll select the units to be metric. In lengths we have two options, either we can select centimeters or meters. So assuming our distances to be in meters. Then forces, again we have two options, newtons and kilonewtons. So this is pretty basic. Then let us go to this second option. Here if we can see, if I click here on this M button, I get this pop-up window where I can actually input the mass of my system. Now before going to this, there are two ways in which we can enter our mass. Either I can enter the mass in terms of kg and tons, or I can enter its equivalent weights in newtons and kilonewtons. So for that we'll go to this parameter option and then input mass as, we have two options. If we select this as mass, then in the mass window we'll have to enter the mass in terms of either kg or tons. Similarly, if I select weights here, I'll have to enter the equivalent weight of that system in terms of newtons and kilonewtons. So let us select mass. So I'll have to enter my mass in terms of kg or tons. Now how to decide whether we have to enter it in terms of kg or tons? When you select this unit force in as newtons, then our mass is to be entered in terms of kg. If we select this force to be kilonewtons, then obviously our mass should be entered in terms of tons. So if we have kept it as newtons, I'll enter my mass in terms of kgs. If I click here, I'll get one window, and let us say I put some value of mass, say 100 kg. Let us OK. So 100 kg is there. Now for damping, again there are two options. If I go to parameters, input damping as, there are two options. Either I can input my damping in terms of percentage damping, that is 2%, 5%, 10% and so on, or if I have the direct value of that constant C, I can select this damping constant and I can put the values in terms of C directly. So for the time being, let us select percentage critical, that is percentage damping. So here when I click on this button, another pop-up window arises, and here I put, let's say 5%. So 5 indicates 5% damping. So I need not put 0.05, that would have been damping ratio, but here I want to input the values in terms of percentage. So directly 5 I'll put. OK. So this is there. Moving on to this property, I'm skipping this dynamic force application part for the last step. Now going to this property, first we'll select whether we want to analyze it as linear or non-linear. So when you select either of them, we can see different options are selectable and some are closed. So in linear case, if you remember that linear curve for force displacement, we are only interested in the linear spring stiffness. So for the linear case, only one option is available, that is stiffness. So if I click on this button, again one pop-up window arises. Here I need to give my stiffness, and if you remember, our initial force was Newton and length was in meter. So the stiffness is Newton per meter. So again, considering my stiffness to be 100 Newton per meter, clicking OK. Here we can see 100 Newton per meter is there, and linear case. When you put this value of stiffness, mass and damping, directly you can see that it has calculated the uh, periods and frequency for your system. We can cross check for a mass of 100 kg and stiffness of 100 Newton per meter. My period comes out to be 6.28 seconds and frequency would be 0.159 Hertz and so on. Here also we can see the damping corresponding to 5% critical would be 10, mass in newtons would be 980, and it has considered G value as 9.807 meter per second square. Now moving on to force application. Here we have different options. We can analyze this system for free vibration. Let us say I select free vibration and I click here, set parameter option. When I click here, it is asking me starting displacement and starting velocity, that is u0 and v0 values. If I put some values here, maximum duration, that means for how much time I want my analysis to be performed, I can put it here. Okay. So this system is ready for analysis. How can we say that this system is ready? This option, this button, if you remember, earlier it was red. Once you have entered all the parameters, once you have entered everything, this becomes green. That means your system is now ready for analysis. So if I press run, it runs and it is showing what force it has considered at the bottom. It is free vibration case with initial damping and parameters as we have selected. Now to view the results, either we can directly see the main important results here, or we can also see the summary of our results in result tabulation, this option. If I click on this, a new window pops up, report sort of thing. Here we can see our initial stiffness was 100, structure's weight was this much, damping was 5%, and different input parameters which we have given. Then forcing function property, it was free vibration, absolute maximum displacement, absolute maximum value was 0, number of data points it has considered is 2000, and so on. And if we see the summary, that is the output response. So we are interested in this maximum spring force. Maximum spring force. This is the force that is going to be generated in the spring for the single degree of freedom system. So maximum spring force is 100 in this case, and maximum computed displacement is 1 meter. So this is what we are interested in. 1 meter and maximum spring force is 100 newtons. So for the free vibration case in linear analysis, this 100 becomes my F0. So my F0 for this particular case, for this particular loading value or loading function is 100, F0 equal to 100, and U0 is 1 meter. That is maximum computed displacement, U0 is 1 meter. So this is how we perform the linear analysis for free vibration case. Let us look at all the other options which are available. Now another option which is available to us is forcing function. So if I select this forcing function here and again press on this button, a new window pops up. Here I can actually define the different forcing functions that I want. That means I can either select a sine wave or a square wave or a triangular wave, and there are total 5 wave functions which we can define. And if you know, this uses the superposition principle. So if we consider one wave as sine, another wave as square, third wave as triangle, and if we input different parameters here, it will superimpose all the three or all the five, and it will consider the final graph or the final forcing function, that is the combination of all the three. Let us say for the time being I just want a sinusoidal wave. So the forcing function or the force magnitude, let us say I want it as 100. The period should be 1 second. 1 second. See, the natural period of our system is 6.28. So let us consider our forcing period to be 5 seconds. Phase, we'll put it as 0, and duration, so again natural period was 6, so let us consider this to be 60. So up to 60 seconds my forcing function will be there. Now length of signal is 10 seconds, or okay, this is 10. Yeah, okay. Thing is, if we look at this option, length of signal, this is the maximum uh, output or the maximum time period for which we can analyze. If I put this value as 10, the maximum forcing function I can have is 10. Even if I try to put anything greater than 10, let's say 11 here, it won't take it, it won't consider. It will bring it back to 10. Why is that so? Because we have defined that the input signal, maximum length of that input signal is 10. If I want to put my forcing function to be 60 seconds, I should first make this value greater than 60. So let us consider this to be 60 for the time being. Delta t is 0.01 seconds. So it is giving me the number of points. This is similar to the delta t and number of time step as we see in the time history case in SAP. This thing and that thing are similar. So the maximum signal length is 60 seconds. My forcing function can be anything ranging from 0 to 60. So if I put this value as, let's say, 40, so that means my forcing function is applied till 40 seconds, and beyond 40 up to 60 it will consider it to be oscillating or vibrating under free vibration case. So 0 to 40 is forced vibration, more than 40 up to 60 will be free vibration. This is how we can decide. Once you have entered all the required parameters, we'll select this generate signal. Once the signal is generated, to view the time history plot or view the forcing function that we have created, we can click here. This is the forcing function that we have considered. See, from 0 this forcing function starts, it oscillates sinusoidally up to 40 seconds, and from 40 seconds up to 60 the force value is 0. So up to 40 it is a forced vibration, beyond 40 it behaves as if it is in free vibration case. Then, very important, once we have generated the signal, we have to press this button, use for analysis. Unless and until you press this button, this function that we have created won't be used in the analysis. So say I consider or I select this use for analysis, now it is there. And again, if I press this run analysis, it is showing me the results. I can go to my result tab. Yeah, I can go to the result tab here. See, the forcing function has changed. Maximum value of force was 100, maximum number of data points was 6000, delta t was 0.1, so likewise. And again in this case we are interested in maximum spring force. In this case maximum spring force has increased to 288.85. So this value is my F naught. This is my F naught, and maximum computed displacement becomes 2.88. So this is my U naught. So this is F naught and U naught. Similarly, if I want to analyze my system, linear system, under ground acceleration, I can select this option, ground acceleration. Again, when I press this button, set parameters, I'll get this window. Here, I should select open file. When I select open file, when you install NONLIN software, a set of earthquake time histories directly gets installed in your system. We need not install them separately. These are already in your system if you see. While installing this software, these already get installed. So I can select any earthquake data from this given parameters. Let us say for the time being, I select this Imperial Valley El Centro earthquake having number 11_140. I select this, open, and once this is selected, see it is showing where it is stored. C program files, advanced structural concepts, NONLIN, and then this file is there. It is giving all the different parameters. This file consists of 7807 points. Its interval is 0.01 second delta t. Its duration is 39.03 seconds. Maximum acceleration in terms of g is 0.364. So different parameters regarding that earthquake time history that we have selected. Again, once this is done, once you have selected the required earthquake, we need to press use for analysis. Use for analysis. Use for analysis is done. Then we can press run analysis from here. It runs. If I hide my taskbar, you'll be able to see. It has analyzed my structure for this El Centro earthquake that we have selected, and if I go to results, I am able to see the parameters. So again, input parameters remain the same. What we have changed is the earthquake or the forcing function. Now it is Imperial Valley earthquake. Sorry.